Okay, so I wanted to make a short video here about this question, which is what is the point? What is the point of sketching a function? And to demonstrate what I think the point is of sketching a function using what we learned in our class in Calculus 1, I wanted to give two examples. And here's the question. Find the local maximum of these two functions. So imagine, I don't know, you're a business and you have some crazy function and you need to maximize it, right? You want to find the maximum of your profit or something like that. Here's two functions, question one, question two. Think about what is the maximum of these. So I'll give a second for this. This one maybe is a little hard to see. So it goes like this, and then it goes all the way down here, and then it's super flat, like that. And these are plots. I took a formula, I put them into a graphing program, and this is what came out of it. So use the graph to find the local maximum of the function. All right, I'll give you a second to think. Pause the video if you want to think about it. Okay, so hopefully you thought about it, and I think the answer is neither of these functions have a local maximum that you can see. This one just goes off forever. This one goes up here. This one is between -1 and 1, -1 and +1. This one is on a different axis, -100 to +100. But both of them, it looks like there's no maximums going on here at all. So I guess you go to your boss and you say, hey boss, there's no maximum. Turns out you get fired because there is a maximum. And actually, even more surprising, these are both the same function. These are the same function. What the hell? The same function. These are both the function x to the power 100 divided by e to the x. And this function is a kind of a tricky function, and computers just can't handle it very well. This is what you get if you put it into Desmos. So you put it into desmos.com, you get a graph that looks like this. Totally useless graph, doesn't tell you anything about the function. In fact, this graph looks identical to the graph to the power x to the 100. So Desmos cannot tell you the difference between x to the power 100 versus x to the power 100 over e to the x. If you just plug them in, they look the same. Okay, so Desmos, useless. This is Wolfram Alpha, which is smarter. So Wolfram Alpha is a bit smarter, and it figured out that there's something interesting going on over here on the negative numbers, but still doesn't answer our question, where's the local maximum? In fact, this function has a local maximum right here at x equals 100, at x equals 100. And how can you see that there's a local maximum at x equals 100? That's the graphing technique that we learned in class. So by looking at the first and second derivative, you can figure out what this function looks like, and you can do a better job than computer programs. So computer programs, if you give them this function, they won't be able to figure out what it looks like. They don't work because this function it kind of goes crazy on certain parts of the graph, and the graphing program doesn't know where to look. So if you do it our way, the first derivative turns out it's so the function f of x is x to the 100 over e to the x. The first derivative f prime of x is equal to x to the 99 times 100 minus x over e to the x. So you can do it by product rule and simplify a bit. And then from this, you can see that x to the 99, this is positive when x is positive. 100 minus x, this is positive when x is less than 100. So you get this nice table. Looks like this. X equals 0 is interesting. X equals 100 is interesting. You have these functions x to the 99, 100 minus x. E to the x is always positive. That one's not so interesting. So e to the x always positive. X to the 99 is positive for x less than 0. Sorry, positive for x bigger than 0 and negative for x less than 0. 100 minus x is positive, and then negative after x to the 100. And so what you end up with is f prime of x is negative, then positive, then negative. So the function is decreasing, then increasing, then decreasing again. So therefore, x equals 0 is a local min, and x equals 100 is a local max. So because of this going down then going up behavior, you can see that these facts. And that's not visible on the graph. So it's totally true here. The function, okay, I guess you can see that x equals 0. Even that, is it a local min? It looks really flat here. So the graph doesn't tell you that x equals 0 is actually lower than all the other points. So, you know, already we've got something. If you do the second derivative, f double prime of x, turns out it has a nice formula too. It's x to the 98, and then it's x minus 100 minus square root of 100 times x minus 100 plus the square root of 100. So it factors really nicely. Okay, and again, you have to do product rule and figure that out. But again, you get the nice formula, and you know, maybe you do the same kind of table. And I'm going to skip doing the table. Same kind of table. But what you'll get at the end of the day is that the second derivative has it goes positive, negative, positive at these 2 points, 100 minus square root of 100 and 100 plus square root of 100. And that means that the function is concave up and then concave down and then concave up again at these 2 points. So this is 90 and this is 110. So 90 and 110 are the interesting points, and x equals 100 is a local maximum. So these are the points of inflection here at 100, at 90 and 110. So what this is telling you, and it's not super complicated, is telling you that the function actually, what it should look like is something like this. Let me draw a little cartoon of the function right here. So what does the function look like? So it comes down for a while. It hits its local minimum at x equals 0. Then it goes up for a while. It hits a point of inflection at x equals 90. Then it flips to concave down. It goes up to its local maximum at x equals 100. And then it goes down again. Hits a point of inflection at x equals 110. X equals 110. And then keeps going down like that. And you can also show that there's a horizontal asymptote at x equals 0. So the function actually looks something like this. And that behavior is totally not obvious in these computer graphs. So what's the moral of the story? I think we have learned how to sketch functions in a way that is more useful than graphs. Okay, and for some functions you put it in a computer program, it's no problem. But there's tons of interesting problems out there where a computer can't handle it. So you can put it into the computer gives you a graph. The graph is useless. Okay, and actually, once you know where to look for, once you have found these interesting points, now you can tell the computer, hey, please zoom in around x equals 100. I know that's where the interesting thing is. So here's another search I did. Once you've done what I did, you can say, let's look between 60 and 140. And here's a graph of the same function, x to the 100 over e to the x. And now the computer is telling you really something useful. Now you can see what's going on. So you can see the point of inflection, the maximum here as x equals 100, the maximum, the point of inflection at x equals 110, and the other point of inflection at x equals 90. You can really see what's going on. And maybe I'll say one more thing. This is an exciting fact. This curve is very close to a bell curve. Very close to I'll call it a Gaussian bell curve. So there's a theorem in probability called the central limit theorem that says that a lot of things in a lot of complicated functions in real life end up being close to bell curves. And this is one example. So what we did is our analysis tells you where to look, and once you know that, you can prove, you can get an even more refined picture and really, prove using analysis that it's going to look the way it does. So, okay, hopefully you understood my point of view on why we're smarter than computers. All right, I'll stop there.